Welcome to the part 2 of lecture 2. In this model, in this part, we will discuss the model assumptions and how to check the model assumptions. Consider the linear regression model y equal to x beta plus epsilon, where epsilon follow normal 0 sigma square. In this kind of models, we have essentially four assumptions. One is linearity, the first one, and it says data in linear hyperplane, and the second is independence, which essentially says that covariance between epsilon I and epsilon j equal to 0 for all I not equal to j1 to n. Effectively, it is the randomness. We want to check the randomness if the typically cross-sectional data. For the cross-sectional data, we implement the standard linear regression models, and in the standard cross-sectional models, we if you draw your samples in using a simple random sample with replacement kind of design, then you can assume some kind of randomness is there. And if you're not so sure, it is better to check the whether the randomness is there, and if it is a randomness is there, then you can safely make assumptions, these kind of assumptions, that covariance of epsilon I and epsilon j is 0, correlation between epsilon I and epsilon j is 0. The third assumptions that we generally talk about is homoskedasticity, also known as homogeneity, where effectively we try to say that variance of epsilon I is sigma square for all I. And the last assumption, or the fourth assumptions that we check, typically that Gaussian distribution assumptions, that the residuals of the error follows a Gaussian, or the typically known as normal distribution. First, how can you check the linearity on if your data is uh, in a linear hyperplane? One quick way of checking is you do a scatter plot for fitted values against the residuals. If there is no pattern, if there is completely random behavior in the data, in the plotted scatter plots, then you can safely assume that the linear hyperplane assumption or the linear model assumption is reasonably correct assumptions, and you can move on checking second, third, and fourth assumptions. But if this does not hold good, then it indicates that the model is not a right model. You should try some other models. The second you should check for is the test for randomness, or the randomness to check the independence. So the null hypothesis, typically we will assume that the errors, the ei1 hat, e2 hat, en dot 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 en hat, they are random numbers. They're essentially a sequence of random numbers generated by a regular random process, versus these numbers are not random. So the typical tests that are available for us are known as Bartlet's rank test, also known as Bartlet's ratio test, Man-Kendall's Kendall rank test for randomness, and the third one is Wald-Wolf-Ute's run test for randomness. Now, out of these three tests, Bartlet's rank test or the Bartlet's ratio test is supposed to have the highest statistical power, so it is better to use the Bartlet's rank test or Bartlet's ratio test. In R, we have a package called RAND tests, which implement several non-parametric randomness tests of hypothesis. In this package, I have checked these three tests definitely are there. In addition, some other tests for hypothesis for checking randomness in the sequence of continuous random variables. Third assumptions is about homoskedasticity, or also known as homogeneity, and how to check the homoskedasticity or the homogeneity. Now, what is homoskedasticity? When the variance for all residuals are equal, we call that as homoskedasticity or homogeneity. Now, null hypothesis H naught is variance of epsilon I equal to sigma square, I equal to 1 to n. When the variance for residuals are different for at least one case, we call that heteroskedasticity. Null for alternative, we assume that the model is heteroskedastic. So variance of epsilon I is not sigma square, at least for one I equal to 1 to n. At least for one I, variance of I, epsilon I is not sigma square. So equal variances across population is called homoskedasticity or homogeneity of variances. If equal variances does not hold, then it is known as heteroskedasticity or heterogeneity across the population or uh, across the population under study. Now, how to check homoskedasticity? The series of tests can be done. One is Breusch-Pagan test, Bartlet test, boxes M test for homoskedasticity in multivariate data, or equal covariance. Now, how Breusch-Pagan test can be conducted? Consider the general form of variance function. Variance of epsilon I is equal to expected value of EI square. Now expected value of EI is 0, we know that, so it will be expected value of EI square will be some function of gamma 1 plus gamma 2 z2 plus dot 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 gamma q zq. Now we want to test whether gamma 2 equal to gamma 3 equal to gamma q is 0. If all of them are 0, gamma 2, gamma 3, gamma 4 to gamma q, all of them are 0, then this part is effectively 0, then variance of epsilon I is only function of gamma 1. And then basically it says that means homoskedasticity, that it is same for all cases, and at least one gamma is non-zero will indicate that the homoskedasticity is not right assumptions. There is a possible heterogeneity in the data. Note that Z2, Z3, ZQ could be same or different from X1, X2, XP. So you can take the X1, X2, XP as Z2, 3 and Q, or you can do some feature engineering of on X1, X2, XP and take them as Z2, Z3, ZQ. The dependent variable EI square are unobservable. Why? If you go back to your model, you see y equal to x beta plus epsilon, your beta is unknown. If your beta is unknown, naturally epsilon, original epsilons are always unknown. So effectively these EIs are unknown, so we have to substitute it with its least square estimate EI hat square. So effectively we want to estimate EI hat square, we want to model that as a gamma 1 plus gamma 2 z2 plus dot dot gamma q zq plus some new I. Now what kind of test we can do? The Breusch-Pagan test actually conduct a chi-square test, which under the null hypothesis, the statistic is basically n times the r square. R square is the coefficient of variation, which we will discuss about this coefficient of variation very soon. And under the null hypothesis, this chi-square follow a chi-square. This test statistics follow n times r square follow chi-square distribution with q minus 1 degrees of freedom. In R, there is a package called LM test. It contains a function called BP test, or abbreviation for Breusch-Pagan test. You can use this BP test function to test for homogeneity. If you're using Python in stats model module, you have this diagnostics under diagnostic hit underscore Breusch-Pagan. You can use this also in Python to run a Breusch-Pagan test for heterogeneity. Last assumption that we are going to check is check for normality, and one quick way of checking is through a QQ plot of the residuals. So you can plot a QQ plot for residuals, and if all these samples are along the theoretical red line, we can say that normality is reasonably okay with this data. If it deviates significantly from the red line, then we say that hey, it is not perhaps not the right thing to assume. So in this case, we are seeing that some of the points here and some of the points here are actually deviating from the red line. So maybe it's not the right thing. We don't know. We have to check it out. One way of checking the normality is using some statistical test called Kolmogorov-Smironov test. Now, how the Kolmogorov-Smironov test are done? So you assume that your null hypothesis, your error follow normal 0 sigma square. An alternative is the residual does not follow normal 0 sigma square. So the Kolmogorov-Smironov test statistic is defined as Kn equal to square root of Dn, where square root of n times Dn is basically supremum over x, Fn E or minus F phi sigma of E. Now it should be over E actually anyway, where Fn E is equal to 1 by n summation indicator function of Ei, where indicator function Ei is the indicator function which equals to 1 if Ei is less than E and 0 otherwise. It rejects the null hypothesis at level alpha if Kn is greater than K alpha, where K alpha is basically determine the 1 minus alpha level of significance, the critical value at alpha level of significance. Now, fortunately, you don't have to do any of these things. There is a package in R. You can use case.test in the stats package, which runs the Kolmogorov-Smironov test, and it gives you a p-value. And if the p-value is less than some level of significance of say alpha equal to 0.05, then you will reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. In Python, you can use scipy.stats.ks test to run the Kolmogorov-Smironov test. So this is a pretty standard, methodology which are available in most of the, analytics package, R, Python, SAS, MATLAB, any standard statistical um, module or any statistical languages or software will have Kolmogorov-Smironov test for normality. These are very old tools, very used tools, so it must be available somewhere in these softwares. Other than Kolmogorov-Smironov test for checking normality, there are two others tests are available. One is Anderson-Darling test, another is the Shapiro-Wilk test. You can use either of these also in case of Kolmogorov-Smironov test. What happened if any one of the model assumption is not true? If any one of the model assumption is not true, you should not use that model further. You should stop there and you should try some other models. And if you're reporting a model, your final analysis based on a model, before reporting the analysis from that model, you should check all the model assumptions, because if you don't check the model assumptions, you may face a problem later that if any of the model assumptions violates, then you may face some severe criticism for model assumption violations. So before reporting any analysis based on a model, you should check the model assumptions. What happened if all the three main assumptions, including the linearity of the fourth assumption of the model, are good? It's a great news if your model assumptions are good and they're getting satisfied with the data. Then you have overcome one of the big hurdle. Now check how good is your prediction accuracy, and can you improve the prediction accuracy by taking some new predictors, or by engineering some features or something like that. So with that, I will stop this part, and thank you. So next part, we will discuss how do we compare performance of two models, different choices of model selection criteria that can be used to compare the different models. So please continue watching in the part 3. Thank you very much.